Welcome back to Computer Science 252 at the University of Wisconsin-Eau Claire. I'm Jess Friesma, and I'll be giving mini lecture number 5, where we talk about program building and the stages of compilation. The relevant chapter in your textbook or section is 6.1. The self-check questions for today's lecture are pretty simple. How do I compile code? I hope you know that. And what does it mean to pound include something? These are the 4 main stages of compilation. Up to this point, we've pretty much considered compilation to be one thing. You compile your code into a program. But there's actually a number of things going on in between. When we call GCC to compile a program with a main method into a binary, GCC will do it all at once because it contains all of these parts. But under the hood, it's doing these all in stages internally. So we're going to look at what these stages mean and how that might help us build better code. During the preprocessor stage of compilation, the preprocessor will, well, basically just do text substitution. Pretty simple in some ways. But there are some special rules for how to do that, which we'll briefly talk about. If you do this within GCC, you can give it the -e flag, as shown here in red, and it will take your .c file and produce, which contains raw C code, and it will produce what's called extended code, which is still valid C code, but it's got a lot more code than just the code that you wrote, and that will be stored in a .i file. Preprocessor commands. The preprocessor commands, or directives, start with the pound sign or the hash sign. So you've seen the pound include preprocessor command already, but some other ones that are pretty common that you may have seen are pound define, pound if def, pound if ndef, pound pragma, pound endif. There's a whole bunch of commands, and all of these commands are basically telling the preprocessor how do I copy and paste, or how, if, or when should I copy and paste text from other files, from within this file, and so on and so on. The pound include preprocessor directive is the most popular, or the most common and most easily recognized one. It inserts a header from another file. So for instance, if I do pound include standard.io.h, this is going to literally copy and paste the contents of standard.io.h into my program at the point where I pound include it. Now the angle brackets here mean this is a standard header file. It's not one that I've created myself, and therefore you should search in the standard header locations. It's something that's pre-installed with the computer, or pre-installed with the compiler. Now you may also see this, where instead of the angle brackets, you use the quotation marks. And what that means is that this is a custom or a new header file. It's not a standard header file. Therefore, instead of trying to search for it in the standard header locations, in the pre-installed places, instead try searching either the current directory or a special include path that's given to the compiler. Another one is pound define. This defines a preprocessor macro. Here are some examples. So if you want to create a constant that's literally going to be a constant, you can pound define buffer size to be 1024. That means that anytime that you see buffer size like that in your code, the preprocessor is automatically going to do text substitution, find and replace. Wherever there's a buffer size, it's going to replace that with 1024, literally. No compilation happening, it's just text substitution. And then the next one, pi. It'll replace wherever it sees capital P, capital I by itself with that whole number. Just literally verbatim, no compilation, just text substitution. Now those are objects that you can, object macros. You could also do a functional macro. So you can define a quick little easy function. So pound define square if I want a square number. So square parentheses x. It's like a function. It looks like a function. And so if it ever sees the function square parenthesis x end parenthesis, it will take that and literally replace it with double parenthesis x end parenthesis star parenthesis x parenthesis parenthesis. And so it's going to square whatever is inside of that function right there. And it does that in a pretty smart and intelligent way. However, be careful when you do these. And here's another one, min. It takes the minimum, it returns the minimum of 2 numbers. Now, doing functions using macros can be dangerous. It's great and it's awesome if you know what you're doing, but it can also be, there's a lot of pitfalls and there's a lot of ways to misuse it. So if you do that, be careful. If you want more information, there's a great link on the bottom. Some of the most useful preprocessor macros are those that are predefined. So for instance, the date macro. So if you ever see this in your code, it will replace that during the preprocessor stage with literally the current date whenever you preprocessed it. Time, same thing. It replaces it with the current time in that format. You can also see what the name of the current file is. So if I do this in myprogram.c, then __file __ will automatically get replaced with myprogram.c. And then this one right here is one of my favorites. __line ___ returns the current line number in your source code. This is before all the preprocessing happens. So if I do this on line 35, it's going to replace that with a decimal 35, which is kind of cool. What that means, what these last two ones mean, is that you can print an error message in your program that will say, I've got this error at this in this file at this line, which is excellent for debugging. Let's move on to the compilation stage itself. During compilation, the compiler will take the extended code from the preprocessor stage and convert it to assembly language. During this process, it will check the C syntax from your code for errors, and it will try to optimize the code as best it can, and eventually it will take that all and translate it into assembly language and output it as a .s file. Now, if you want to tell GCC to just do that, you can give it the -S flag and give it a .i file, and it will convert that to a .s file. Next up is the assembly stage. In the assembly stage, it will take code written in assembly from the compilation stage, and it will convert that into actual machine language. So before, the assembler code is code that you might not understand, but at least you could open it up in a text editor and you'd be able to read it. But when you convert it to machine code, now it's actually all binary code. And so you could try to open up a .o file in your favorite text editor, but it won't be anything that you can read because it's binary now. The job of the linker now is to take all of the object code generated by the assembler and bring it all together, including any function calls to external libraries that your code may have made, and bring all of this object code together into a single standalone program that your operating system can then run. So it needs to figure out, first of all, what function calls do you make, where are they, and then it needs to bring that code together into a single place and finally package it into a program. It needs to make the code available to your program. If your program consists of one file that only calls functions that you define in that file, then the linker doesn't have to do a lot of the work. A lot of the work has already been done by the assembler. However, if you call functions like printf or cosine, then the linker needs to figure out how do I make those functions available to your program. And it can do that in one of two ways. The first is static linking. So static linking will look to a statically linked library, which are .a files in Linux or .lib files in Windows. And a statically linked library, or static library, is a bundle of object files all together in one single file. So what the linker will do is it will go to that file, it'll look up the command that it needs to do, the function that it needs to copy, and it will copy it from there into your executable. So the linking is going to happen right at this stage during this whole compilation process. Because it copied that code into your file will be more standalone. It doesn't need to look for other places, other functions elsewhere in the system. It has all the code that it needs in itself, but that also means that it will produce a bigger file size. The other method is dynamic linking. So dynamically linked libraries, which are .so files in Linux, .dll in Windows, they're kind of similar, except what's going to happen is the linker is going to, instead of copying the code into your program, into your executable, it's going to make a little note in your executable where to find that code on your computer system. So as the computer runs your program, it'll eventually get to this little message and say, hey, you called the printf, or the programmer called the printf function here. And so then your computer will have to go, or your program will have to basically have a go-to statement to wherever that printf function is elsewhere in the system, run that bit of code, come back to the same place in your program, and then carry on. So that means that linking is happening at runtime rather than at the compilation stage. And it also means that your program will be the file size will be a little bit smaller because it didn't need to copy that code in. It also means, however, that it's going to be dependent on that file existing. If that file gets moved or damaged or corrupted, then the programs that were linked dynamically to those libraries won't be able to work anymore, which is a problem. So in summary, or in review, I should say, what are the 4 stages of compilation? Can you name them? Do you remember what files are produced at each stage? Also, what are the differences between static and dynamic linking? What are the benefits? What are the disadvantages? And for practice, I challenge you to write a simple hello world program in C, and then using these slides or the instructions at these links here to go through each stage of the compilation separately for your hello world program. First, preprocess it, then look at the output of the preprocessor, then compile it, look at the output of the compilation stage, and then assemble it, and then look at the output of the assembly stage. Can you find the hello world text in each one of these? And then finally, link it, and then run the program and see if it worked. That's all for now. Thank you for your time, and I hope you have a great rest of your day. Bye-bye.